Hi, everyone. Welcome to Configuring MDM Matching Rules. My name is Rafiq Durawoju. I'm a principal consultant at Ataccama, and I'll be leading you through today's session. So today we'll be breaking down fuzzy matching rules, and we'll be using these rules within the Ataccama matching step and the overall Ataccama context. In terms of the training agenda, first we'll focus on specific approximate or fuzzy matching rules. Then we'll discuss the fuzzy matching rules within Ataccama and look at specific examples of the fuzzy matching rule logic, after which we'll look at examples of the Ataccama matching step implementation. Then I'll open up the floor for questions and answers. So when we are talking about approximate or fuzzy matching rules, we're talking about matching criteria where we're not looking for exact matches, but we're actually setting up differences within a threshold that we are comfortable with. So the four fuzzy matching rules we'll be discussing today are edit distance, Levenstein, Hamming, and Yarrow-Winkler. So starting off with edit distance. Edit distance counts the minimum number of operations required to transform one string into another. Now this includes insertion, deletion, substitution, and transposition of two adjacent characters, which essentially means swapping the positions of two characters that are right next to each other. Now, to use the edit distance expression within Ataccama, you would provide two strings as well as two optional parameters, one being the max distance and the other being the case-insensitive Boolean flag. The max distance can be used to determine an upper limit, after which the expression stops looking for differences, while the case-insensitive flag can be used to determine what is considered a difference when looking at two characters of different cases, so uppercase or lowercase. The max distance setting can be used to set an upper limit, which can help with performance, as the expression would stop looking for differences once it's reached its threshold or max value. So now let's look at some specific examples of edit distance. So here we have two words, mitten and sitting. So first, I'll let you have a couple seconds to make your best guess as to what you think the amount of differences are here. So let's see if you're correct. So first, we substitute the M with an S. Then we substitute the E with an I. After which we insert a G to the end of the string. And now we've gone from mitten to sitting, and we've identified three differences. Now, edit distance is typically used for short strings where you expect a small number of changes between the two data sets that you're comparing. So now let's look at Levenstein. Levenstein counts the minimum number of single character operations required to transform one string into another. And this includes insertion, deletion, and substitution. Similar to edit distance, Levenstein requires the two strings and the two optional parameters, max distance and case insensitivity. Now let's look at the differences between Levenstein and edit distance. Levenstein considers single character operations, whereas edit distance considers multi-character operations. So they both include insertion, deletion, and substitution, but only edit distance considers transposition. Both functions are often used for name approximate matching. So this includes first, middle, last names, where we have, or in cases where we expect human data entry, which can be prone to errors. So let's look at some specific examples where we can compare the edit distance difference versus the Levenstein difference. So here we have two spellings of Michael. and this could represent such data entry where there's a human error in the spelling of a name. So here you can pause the video and you can look at and you can make your best guess as to what the differences will be for each expression. So let's look at edit distance. So here, all we have to do is transpose the A and the E to get the two strings to match, which gives us a difference of 1. And for Levenstein, here we delete the A, then we insert the A back in front of the E, as Levenstein only considers single character operations, which gives us a score or difference of 2. Now, as you can see, edit distance and Levenstein are very similar to each other, and they can be used interchangeably, but you need to make a decision whether you prefer to consider transposition as one difference or two differences. Now, when deciding on which data or which fields to use edit distance or Levenstein matching expressions on, it's worth considering that the longer the strings that you're comparing with, the higher the computational cost. So that is why these expressions or these fuzzy matching rules are typically used on short strings, because the cost is relatively proportional to the length or to the product of the length of both strings. So the longer the strings, the more the computational cost. So next, let's look at the Hamming expression. Hamming counts the minimum number of substitutions required to transform one string into another. So this is only used for strings of the same length, as we are only able to use substitutions here. So for the Hamming function, we provide the two strings and a Boolean case insensitive flag, which is once again optional. So let's look at specific examples for the Hamming function. Here we have two words, Caroline and Catherine. And you can pause the video here and make your best guess as to the amount of substitutions it will take to go from one word to the other. So first we'll be substituting the R with the T. Then we will substitute the O with an H, followed by substituting the L with an R. And now we have the same word with a difference of 3. Now, due to the nature of the Hamming distance function, where you require equal length strings for both data sets that you're comparing, it might be harder to find an application for the function. An example of a niche application could be a code set that you have that fits within your reference data to translate to some other meaning. You might now have some codes that come in that your reference data does not recognize, and you might identify those as human error data entry. You can use the Hamming function to essentially find the best guess code that was meant to be inputted rather than the ones that you received, because this code setting, you'd expect the codes to come in with equal lengths. So now we'll look at a slightly more complex fuzzy matching rule, or let's say a distance calculator. The Yarrow-Winkler function uses a prefix, which gives better ratings to strings that start with the same matching characters. The result of the Yarrow-Winkler similarity in this case is a scale of 0 to 1, where 1 is an exact match and 0 is no similarity. Now, the overall score is calculated based on a mathematical function, which we will go over soon. But within Ataccama, you can use the expression by providing the two strings, and then you have the 3 optional parameters that have already been set for you. First is the usual case insensitive flag. Then we have the boost threshold and the prefix length that have been chosen to be the ideal numbers for the Yarrow-Winkler function, which is 0.1, and a prefix length of 4. So Yarrow-Winkler, similar to the other fuzzy matching rules, is also suitable for evaluating short strings. And the distance is actually calculated by taking 1 minus the Yarrow-Winkler similarity score. So we'll be breaking down the Yarrow-Winkler similarity into 2 pieces. First is the Yarrow similarity in itself. So here we can see the mathematical function, and we'll be breaking down what each variable represents. So here we can see the absolute of SI, which corresponds to each respective string, is the length of each string. M represents the number of matching characters, while T is the number of transpositions. Now, those two things are related, and 2 characters from each respective string are considered matching only if they are the same or they're no further away from each other than the maximum length between the 2 strings divided by 2 minus 1 character apart. Now, this is not a math class, so we will not be delving too far into the mathematical proof or solution behind it, but we will be looking at how this calculation works in practice. So here we have 2 words, crate versus trace. Both words are 5 characters long, which means we have 5 over 2 minus 1 equals 1 is the maximum amount of differences that we can have to consider two characters as matching. And as you can see here, we have R, A, and E matching. So we have an M value of 3. But C and T are more than 1 character away from each other, so transposition does not consider them matching this case. So we have a T value of 0. We pop that into the calculation, and we get a score of 0.733 in terms of similarity. So now let's look at another use case. Here we have 2 spellings of Dwayne. And here the first string is the longer of the 2. So we'll be taking the length of that string, which is 6, divided by 2 minus 1, which gives us a value of 2. So here we can see that D, A, N, and E match. And N and E match because they are only 1 character away from each other in order to match with the other string that we're comparing to. So they're close enough to identify as a match. So we have an M value of 4 and a T value of 1. So this is the amount of transpositions that we actually had to do, which is the N and the E. If we pop that into the equation, we have a value of 0.739. Now, the Yarrow-Winkler similarity takes that result that we've just seen and adds a prefix booster. This is done by taking a product of the length of the common prefixes at the start of 2 strings up to a maximum of 4 characters and multiplying it by a scaling factor. Now, this product are used in such a way that the overall Yarrow-Winkler similarity is never meant to exceed a score of 1. So if we look at the 2 cases that we just had before, where we're comparing crate and trace, we'll see that here, because we don't start with any of the characters matching at the beginning of the word, we don't have any boost and we have the same score of 0.733. But for Dwayne, since we have D starting both characters, we do get a prefix boost and we have an overall score of 0.765. So this is essentially the Yarrow-Winkler similarity. And like I mentioned, the difference is calculated by taking 1 minus the score that is returned. So as you can see, the Yarrow-Winkler function lends itself to more testing and iteration because there's no real standard way to identify the difference as you could with edit distance or Levenstein. So it is one that is definitely recommended to be used and tested and retested, and to make an iterative process in order to find the appropriate threshold for your data set. So now let's shift focus a little bit into fuzzy matching within the matching step. Now, those of you who are here are probably already familiar with using the matching step within Ataccama, so you're familiar with setting up a matching rule. If you've ever set up a matching rule, you'll see that there are out-of-the-box functions that are available. That includes the equality, which looks for a standard equal match between two strings or two values. And then we have the 4 fuzzy matching rules that we've been discussing: edit distance, Levenstein, Hamming, and Yarrow-Winkler. Now, on the limit column, you can set the maximum tolerance of differences for that function. So if the two strings or two values that you're comparing exceed that limit, it does not count as a match. But if it's beneath or meets that limit value, then it'll be considered a match. If the relative Boolean field is checked, the result or the differences between the two values that you're compared is actually divided by the longest of by the length of the longest of the two strings, which normalizes the final value between 0 and 1. Now, as the Yarrow-Winkler function already returns a value between 0 and 1, you do not need to check the relative flag. And if you were to actually to check it for the Yarrow-Winkler function, then the step would give you a warning telling you that the Boolean flag you've checked is redundant. Now, in terms of the fuzzy matching step, most of you are probably familiar with the outputted columns, but these are the breakdown of these columns. First, we have the ID column, which is essentially the unique ID for each record that is now going to be matched together. We have the master ID column, which is the grouping ID for columns that have been found to match together. And then we have the match rule name column, which gives you the name of the first successful matching rule that will be stored. And if we're using the next column, which is the matching quality column, it can actually interfere with which of the rules will be written into the match rule name, but we'll go into that in further slides. But the matching column is essentially the strength of the match, where it is a number between 0 and 1, and 0 is closest to a perfect match. The match-related ID houses the ID of the record to which another record is matched to. And the rematch flag is a Boolean value that is used to identify a record that has been matched before, but needs to undergo another rematch or another matching process. Whereas the isolate flag is used to identify records that should not take part in matching at all. Now, to go into more details about the matching quality column, essentially within a matching rule, if I go back one slide, within a matching rule, you can have multiple tests, and each test will actually have a score, which is determined by, in the case of fuzzy matching, the actual distance divided by the limit. Now, the overall matching rule will also have a matching quality score by taking the overall scores of each one, whereas for equality functions, the score is always 0, but it will take the overall score and divide it by the amount of tests that you have in that matching rule. So now that we've discussed these fuzzy matching rules, we've discussed the Ataccama matching step, it's time for us to actually test some matches. So if I were to switch to the IDE, here you would see a sample plan that's been set up. And we have here the summit data, which I created for this use case. And you'll see there's some human error entries here. And we will be looking at how we can use these fuzzy matching rules to get some matches. So the first thing we'll be looking at here is the setup of the matching step. So here I've set up my matching step where I have no partitions. My key rule is set to be true, so all the records can participate in one match. And here I've set up two matching rules. First is the first name using the Levenstein function with a limit of 1, and my last name and birth date being an equality. And I've also set up an edit distance with a limit of 1. So if I were to run this plan, I'll see from my results here, I only have the one match, which is Eric, where I have this transposition of the I and the C, which gives me a overall match or fuzzy match. For the match quality, you can see how this was derived as I had one difference, which was divided by my limit, which gives me 1. And I have a total score of 1 divided by 3, which gives the overall score of 0.33, repeating. Now, if I were to go into this matching step and I were to change the Levenstein limit to 2, and now we're to run this function again, essentially now you can see that it is using the Levenstein function because it was the first rule that was set up in my matching step and they have the same score. So no need to use the other one. And I actually have another match here, which is Patrick and Patricia. And you can see the overall difference is 2 as I substitute the K with an I and insert an A. So if I were to make another change by going to the edit distance and switching my limit to 2, and running this again, here I can see that I have the edit distance score for my first match. And you can see that it used edit distance even though Levenstein is still applicable. This is because the match quality is actually a lower score, which means it's a better match. So this is because the difference is considered 1 and the limit I set is actually 2. So that is 0.5 divided by 3, which then gives me 1/6 rather than 1/3. So we can see the match quality here. But here, since they have the same matching scores, as this would still be considered as 2 differences in the edit distance, it sticks with the Levenstein as the result. So here we've seen using 2 fuzzy matching rules within a matching step with the overall distance or differences set as an absolute limit. Next, we'll be looking at cases where we've actually set up the relative Boolean. So similarly to the other setup, I have the 2 matching rules here, the first being Levenstein and the other being edit distance. For Levenstein, I have a limit of 0.1, whereas edit distance, I have a limit of 0.3. So you can think of these as more of percentages where we're saying we expect 10% difference or 30% difference overall threshold limit. So as I've already run this multiple times, I have the results available. And you can see that here I have the similar join for edit distance, as well as a similar score for the, or similar matching rule for Patrick and Patricia, where it's both edit distance. Now, the match quality here is a little bit more tricky to calculate, as we are now taking the edit distance score that's been normalized, dividing it by our normalized limit, and then dividing that by the total amount of tests that we have within our matching rule. So you can see where the match quality might be a bit trickier to sort of reverse engineer when you're using the relative field versus when you're using the absolute limits or absolute values for your limits. So now let's look at a third use case, which is using the Yarrow-Winkler function. Here I have 3 matching rules. I have the Levenstein, I have the edit distance, and I have the Yarrow-Winkler. So you can see for Levenstein edit distance, I have my same limits of 1. And for Yarrow-Winkler, I've actually really reduced the threshold where I'm saying here I can have about an 80% difference for Yarrow-Winkler. So as I already have the results for this, if I were to open it up, you can see now I actually have 3 matches. So I have the similar Eric one, which is what we've identified as a probable or a good match. We have Patrick and Patricia, which is another match that matches up with what we have with our edit distance or Levenstein. But here we have another one, which is John and Jonas, which might not be as good of a match regarding the differences in name. It's more than likely not an entry error. So here we can see, once again, the score is a little bit harder to determine. And obviously the looser your threshold, the lower amount of differences you have, the better your score will look overall. But if we were to tighten this up and we were to change the threshold to about 50%, in order to run this step again, here we can see we still have our similar matches, but we can see the scores are actually increasing as the threshold or the criteria for which we consider a match is now increasing. So if I were to go one step higher and I went to 0.1, now we're to run this again. Now I can see that I've actually lost that match between John and Jonas, which is probably a fair shout. But we still have the other matching rules that map with Eric and Patrick and Patricia. So this is an example of the iterative process that you might experience with the Yarrow-Winkler, where you're looking to identify what you actually consider a good enough or an acceptable threshold. And one way that you can actually use this while being able to implement this solution in let's say an environment or a server rather than with dummy data or local data is by leveraging the proposal rules, where within the actual rules, you can set a more stringent limit for yourself, but you can actually set up a proposal rule section that actually has the more relaxed version of that same rule. So by doing this, you essentially allow the rules that don't match by the strict criteria or limit to be processed by the proposal rule. Once you've monitored and looked at the outputs of the proposal rules, you can then decide whether to actually promote that proposal rule to an actual rule. So that is one way that you can have this iterative process of determining what is a good approximate match for your use case. So the next thing that I wanted to talk about was essentially custom functions within the matching step. And essentially these custom functions give you the flexibility in using the approximate matching functions within Ataccama. And I think it's best to actually deep dive into this one. So if I were to go back to this matching step, you'll see here I've created some match function or custom function. And those of you might be familiar with what this looks like. It closely mimics what you'll find in the CDI examples once you've spun up the demo MDM project. And essentially what you have here is a custom function that's actually leveraging a set function with an expression set to it, where we are actually considering multiple words within a value. So rather than using the fuzzy matching for short strings like we've typically been doing so far, we can actually use this for something like a description value of 2 data sets. And we can actually set per word what we consider our leniency regarding a difference between the 2 records. So first, let's look at the function that we build within this custom function in itself, which is the symmetric difference function. And the best way to sort of understand this is to input some values and see what we get back. And we will do just that. So here we have the symmetric difference. where we say if the two values are the same, then obviously it's an equal match. Otherwise, we look to see that they start with the same letter, at which point we go into our case statement. If the length of one of the strings is less than 6, then we actually expect an equal match. But if it's between 6 and 10, then we expect that the Levenshtein, we will give it a Levenshtein difference threshold of 1. And if it's longer than 11 or equal to 11, then we'll give it a threshold of 2. So if I were to put in some values here, in here, so here we can actually see that these two values are not the same, but because it's longer than 6 characters, then we actually give it the leniency of 1 difference. So another example use case we can have here is now we have essentially a transposition. And here you can see that the symmetric difference has now been identified as 2 because these two characters are different and because we're using the Levenshtein function. Now, if I were to actually use a different function in this case, let's say the edit distance, now I can see that I get a score back of 0, and that's because we only consider the transposition to be 1, a difference of 1 within the edit distance function. So that's an example of how you can use different functions to sort of determine what you consider your best case leniency is. So if I were to return this to the original value, we can now look at the overall function in itself. So essentially here, we look at the word count of the actual string that we're going to be using for comparison. And we say that if it's less than 2 words, then we consider the symmetric difference score we get back to be 0, or we have no leniency in the amount of symmetric differences that we can expect. And this is essentially a result of this fuzzy function here where we might actually still have differences, but we are lenient against it and we'll consider it not a difference. But we're saying if we have a word count of less than 4, but more than 2, then a symmetric difference of less than 2. But if I were to actually make this less than or equal to 2, then we have a little bit more of a threshold here. And if I were to debug this, and I were to put in, this is allowed ingress. So here, essentially, we have the difference between ingress and egress. And we can see because this is 4 characters long, we've essentially decided that we have this threshold of less than or equal to 2, which is fine here because our symmetric difference here, it actually returns a value of 2. Because we have a threshold of 3 rather. So here the symmetric difference returns 2. So we are within our allowed difference between the two values. So this is a somewhat complex use case of using a custom function where we've actually leveraged the fuzzy matching functions or expressions that we've been discussing. And you can actually use it for, let's say, longer strings or longer data sets than just the short strings that we've been discussing so far. So that concludes what I wanted to discuss in terms of the custom functions. And I hope you've come away from this having a better understanding of fuzzy matching rules, of understanding the applications both in and outside of Ataccama, and you feel more comfortable in terms of experimenting with fuzzy matching rules within your data sets. Thank you very much.